Welcome to the deep dive. Today, we're really tearing into the core recipes of computing algorithms.
Yeah, it's
I've
true.
got this stack of BTEC notes here on standard algorithms. And, well, our mission is to cut through the jargon, the instructional stuff, and just get to the pure insight.
Yeah, the aha moments.
Exactly. We want you to walk away understanding not just what these things are, but really why picking the right one makes such a difference. You know, the difference between an app that flies and one that just crawls.
That's definitely the key tension. An algorithm is, fundamentally a set of instructions, step by step, things a computer follows to solve a problem.
Right, the recipe analogy.
Precisely.
Yeah.
But the definition isn't the tricky part for anyone following this topic. It's the scaling part. Giving a computer, say, 100 steps for 10 bits of data, fine.
Okay.
But what if that data jumps to 10 million bits? Does that recipe suddenly need 10,000 steps? Or 10 billion? That choice, the algorithm choice, dictates everything.
So efficiency is the name of the game. We're diving deep into the main categories from your notes: sorting, searching, and then those data structures, stacks and queues.
Makes sense. Let's start with sorting. That's where the organization begins, really. It's just arranging data in a specific order.
Alphabetical, numerical, smallest to largest.
Yep. And this choice, how you sort, probably has the single biggest impact on program speed, especially when you're wrestling with, huge amounts of data.
Okay, let's compare them then. Your notes highlight three main ones, starting with
Bruh.
the simplest one, bubble sort.
Ah, bubble sort. Everyone codes this one first, I think. It feels intuitive, definitely. But that simplicity hides a pretty big flaw.
Tell us how it works, though. It goes through the list again and again, right? Comparing pairs next to each other.
Exactly. Adjacent pairs, if they're in the wrong order, swap them.
And you can sort of picture the biggest unsorted number bubbling up to the end with each pass.
That's the visual, yeah. The problem isn't the swap, it's how many times you might have to do it. The repetition. If your list size doubles. Uh-oh.
The time bubble sort takes doesn't just double.
Mm-hmm.
It's like quadruples or worse.
Right. That's that quadratic relationship you mentioned.
That's it. It's great for teaching sorting logic, absolutely.
Uh-huh.
But for actually sorting lots of data in the real world, almost never used. It just doesn't scale up.
Okay, so not bubble sort for big tasks. Which brings us to the one that usually gets called the superstar, quick sort.
Quick sort, yeah. This is often the go-to when you've got a big, messy, unsorted list and you need speed.
How does it work differently?
It's based on this idea of divide and conquer. It picks one item from the list that's called the pivot.
The pivot, okay.
Then, really quickly, it shuffles everything else around. Everything smaller than the pivot goes to one side. Everything larger goes to the other side.
Okay, that sounds efficient for one step. But how does the whole list get sorted?
Ah, that's the clever part. Recursion.
Meaning it calls itself. Exactly. Once it's split the list around that first pivot, it treats those two smaller chunks, the less than group and the greater than group, as brand new sorting problems. And it just repeats the whole pivot process on them.
Ah, I see.
And it keeps doing that, recursively sorting smaller and smaller bits until, bam, the whole thing is in order.
So it breaks the big problem down constantly. That sounds much faster. But wait, you said usually fast? Is there a catch?
Yeah.
What if it picks a bad pivot, like the smallest number every time?
That's a really important point. You've hit the worst case scenario right there.
Okay.
While quick sort is typically incredibly fast if your data is already kind of sorted, or if you consistently pick terrible pivots like the very first or last element in an already sorted list,
Yeah.
its efficiency can just plummet. Theoretically, it can become as slow as bubble sort.
Wow.
Most serious implementations have smarter ways to pick the pivot to try and avoid that trap. But yeah, it's usually quick, not always lightning fast. There's a nuance there.
Got it. So we have slow and simple bubble sort, and usually fast, but sometimes tricky quick sort. What's the third one? Insertion sort.
Insertion sort. Think about how you sort playing cards in your hand.
Okay.
You pick up one card, it's sorted by itself. You pick up the second card, you slide it into place relative to the first one. Pick up the third, find its correct spot among the first two.
Ah, okay. You take one new item at a time and just insert it into the right place within the part you've already sorted.
Precisely. Now, its real strength isn't massive, jumbled lists. Quicksort wins there.
Where is it good?
It's actually really efficient for small lists, and crucially for lists that are already mostly sorted. If you only need to shift a new item one or two places back to get it right.
Then insertion sort is quick because it doesn't do loads of unnecessary check.
Exactly. It finds a spot and puts it there quickly. Very little overhead in that nearly sorted scenario.
Okay, that covers the sorting toolkit nicely. But it raises the question, why sort in the first place? I mean, it's effort.
Ah, well, it's often all about enabling super fast searching later, finding what you need quickly, which takes us nicely to searching algorithms.
Finding the needle in the haystack.
Yep. And how fast you find it depends entirely on whether that haystack is, a neat pile or just chaos.
Let's start with the basic way, the chaotic pile approach. Serial search or linear search.
Linear search, yeah, that's the simplest strategy, maybe the most exhaustive.
How does it work?
You just check the first item. Is it match? No. Check the second. Match? No. Third, you just go one by one, start to finish until you find it or you run out of items.
Like looking through a phone book name by name from page 1.
Exactly like that. It's simple to understand, simple to code, but imagine that phone book has a million names.
Yeah, it's going to take a while.
It scales linearly, double the items, double the maximum search time, potentially. Now, if you invested the effort up front to sort that phone book, say using quick sort,
Then you unlock something much better.
then you unlock binary search. This is the big leap. But, and this is critical,
It only works if the data is already sorted, perfectly ordered.
absolutely crucial prerequisite.
Okay, how does binary search work then? It sounds faster.
Oh, it's exponentially faster. Think about guessing a number between 1 and a million. You wouldn't start guessing 1, 2, 3.
No, you'd get the middle, right? 500,000.
Exactly. And if they say higher, you instantly know the answer isn't in the first 500,000 numbers. You've just eliminated 500,000 possibilities in one guess.
Okay, I see.
Binary search does precisely that. It looks at the middle item of the current range. Is it a match? Great. Is the target higher? Throw away the lower half. Is it lower? Throw away the upper half. And repeat.
So it keeps having the search space.
Over and over. To search that list of a million items, binary search needs what, maybe 20 guesses maximum? Compare that to potentially a million checks with linear search.
Wow. Okay, the efficiency gain is enormous.
Staggering. That repeated halving is fundamental to how we find data quickly in computing.
The lesson really is preparation, the sorting, is key. Okay, we've done the processes, sorting and searching. Let's look at the containers that hold the data. Data structures, stacks and queues.
Right. These aren't algorithms in the same way. They're more like specialized containers, ways of organizing data that enforce specific rules about how you add and remove things.
And those rules are LIFO and FIFO.
LIFO and FIFO, last in, first out, and first in, first out, they define the behavior.
Okay, let's start with FIFO. First in, first out. That sounds like a line or a queue.
Exactly. That's the perfect analogy. FIFO describes a queue. Think of people lining up for a bus or jobs waiting for a printer.
The first one in the line is the first one to get on the bus or get printed.
Precisely. Items are added to the back, on queue, and removed from the front, dig you. Essential for anything that needs to be processed in the exact order it arrived.
Makes sense. So what's its opposite? LIFO, last in, first out.
LIFO describes a stack.
Like a stack of plates.
Perfect. Imagine stacking clean plates in a cafeteria. You put a clean plate on top, the next person takes.
The top one, the last one that was put there.
Exactly. Last one on is the first one off. That's IIFO.
And where are stacks used in computing?
Oh, all over. Think about the undo function in software. Every action you take gets pushed onto a stack. When you hit undo, it just pops the last action off the top.
Clever.
Also, managing function calls when a program runs. When function A calls function B, B gets pushed onto the call stack. When B finishes, it's popped off and control goes back to A. Last function called is the first one to finish.
Okay, and the source material makes a point of saying queues are always FIFO and stacks are always LIFO.
Right. Yes, that distinction is fundamental. The structure dictates the order of operations. FIFO is the rule for queues, LIFO is the rule for stacks.
Got it. Now, before we finish, your notes mentioned a couple of other standard algorithms. Counter-occurrences seem straightforward, but input validation, that sounds important.
Oh, it's absolutely critical. Input validation is like the bouncer in the door of your program, the gatekeeper.
Why is just checking the input so vital? Seems basic.
Because without it, your system is wide open to, well, chaos and attack. Input validation is the algorithm, the set of checks that makes sure any data coming into the system.
Like from a user typing or another computer sending data.
Yeah, anything. It checks that the data meets the expected criteria before you try to process it. So if you're asking for an age, it checks if the input is actually a number, if it's positive, maybe if it's less than, say, 150.
So it stops garbage data getting in and causing errors.
That's the first part, preventing crashes from bad data. But the really crucial rule today is security.
How so?
Well, what if someone tries to type computer code into a box that's expecting a name, or they enter a super long string of text into a phone number field to try and overflow things?
Oh, okay.
Proper input validation catches that stuff. It sanitizes the input. If it doesn't catch it, the program might crash, leak data, or even worse, let an attacker run malicious code. It's absolutely fundamental for data integrity and preventing hacks.
Right, that really underlines why these standard algorithms are the bedrock of reliable software.
Definitely. We've kind of journeyed through the core cookbook, haven't we? The efficiency leaps with quicksort, the incredible speed of binary search once things are ordered.
Yeah, and the structured discipline of stacks with LIFO, queues with FIFO, and that crucial gatekeeper role of input validation.
It really shows how choosing the right tool, the right algorithm, fundamentally sets the performance limits for any software you build or use.
Understanding these choices is really the difference between, like you said, fast, reliable code and something slow and frustrating.
And that brings us to a final thought, something for you to chew on. We saw how amazingly fast binary search is, maybe 20 steps for a million items.
Yeah, but only if the data is sorted first.
Exactly. And sorting a million items, even with quicksort, takes significant effort. So the question is, where's the real cost of finding information quickly hidden? Is it the sorting effort up front, the preparation, or is it the search itself, even if it's fast?
The cost of organizing versus the cost of finding.
Think about that trade-off. That invisible work needed to make instant access possible the next time you search through a huge database or your photo library. Where does the real computational effort lie?